Okay, I hope I'm audible to you and my screen is visible. I welcome you all to the 10th tutorial of this course, Reagents in Organic Synthesis, which is conducted by NPTEL, whose course instructor is Professor Subhas Chandra Pan from IIT Guwahati. I am Deepika, your PMRF teaching assistant. I'm doing my PhD in chemistry at IIT Bombay. So, initially in this week, we have already conducted another session which was for week 9 because in the last week we could not conduct the tutorial on Friday. So, that is why on last Monday we had done a compensation tutorial session. So this session is for week 10 and there were two video lectures for this course provided by Professor Pan sir, and I hope you all have gone through the video lectures where we had again discussed a few more organometallic reagents, and in this week we have discussed a lot of new reactions like hydroalkoxylation, hydroarylation, hydrosulfonylation, etc. So let us go through today's tutorial questions which would give you better understanding of the topics. So this is the first question of today's tutorial. And this question is from the topic gold based organometallic reagents. Okay. So you can see you are given a substituted aniline here and you have to react it with a terminal alkyne in presence of gold catalyst and silver triplet additive. Reaction is in room temperature using no solvent, okay? And if you look at the product, you can see that this aniline has gotten cyclized and the amine has also attached to the alkyne given. Okay, so the net result is you can see that this amine is attached to this carbon of the alkyne fragment along with its attachment to the alkyne at this position. Okay, so let us see step by step what mechanism this reaction is following. Okay, it is going to involve basically activation of alkyne mechanism using gold catalyst. Okay, so let us start the mechanism from here. Okay, from here we are going to start the mechanism. So you see gold catalyst first will add up to the terminal alkyne. Okay, and it is basically going to activate our terminal alkyne in this way. So you will get a coordination complex between the gold and the terminal alkyne of this type, which is now going to react with the aniline. So you see this alkyne is activated, because of which the lone pair of the aniline is going to attack at this position, because see your alkyne is of this type, okay, R dash, and when it coordinates to the gold metal, there are two possibilities of carbocations that you are going to get in the course of the reaction. One will be at this carbon and the other will be at this carbon. So if we write the types of carbocations that you can get by coordination with the gold catalyst, one type of carbocation will be here and the second one will be generated here at the outside carbon along with the bond formation with gold. Here, this carbon will form bond. Okay, so if you look at these two carbocations, which one is more stable? Definitely this one, because this is going to get electron density donation because of the presence of electron donating group R dash. Okay, so this is why the aniline which is incoming is going to attack at the more stable carbocation to give you this intermediate 3. Okay, so this imine we are going to generate by the reaction of the gold activated alkyne and the aniline. So after the formation of this imine, now the second step will happen, which is cyclization step. And in the cyclization step, you will see that again we have another molecule of alkyne. Now this alkyne will get activated by gold. Okay, like here you see this alkyne is now going to be activated by gold. And in this case also you can see that two types of carbocations can form. Okay, in this alkyne also, this is one possibility of formation of carbocation and this is the second possibility of formation of carbocation. But this time you have to see how many membered ring you are going to get. See, if this imine attacks at carbon number 1, you will get a 5-membered cycle. Okay, the reaction will be 5 endo dig. Okay, 5 endo dig cyclization will be followed when it attacks carbon number 1. But if it attacks carbon number 2, you will get 5 exo dig. Okay, and if you see Baldwin rules of cyclization, if you remember by Baldwin's favorable and unfavorable rules of cyclization, 5 exo dig cyclization is forbidden. Okay, so out of these two possibilities 1 and 2, you have to go for the cyclization at carbon number 1, which is going to give you a 5-membered ring of this type. Okay, and talking about the cyclization, the imine arrow pushing you have to show in this type. Okay, so this is how you are going to get this cyclization reaction, where you are seeing that in the first step activation of the terminal alkyne is taking place, followed by the attack of aniline, and intramolecular cyclization, which is 5 endo dig cyclization, that happens to give you this 5-membered, basically substituted indole you are going to get. Okay, so this is the mechanism that this reaction is going to follow. Then let us come to the next question. So here again we have an alkyne which is containing a cyanide substitution in its side chain, and also the second molecule is amine. Okay, primary amine. And if you look at the catalysts present, this is a combination of gold and zinc metallic catalysts. Okay, and the reaction is in dichloroethane solvent at 60 degrees Celsius temperature. So we have two different types of products which are going to form here. Okay, in one case, if you see, this pyrrole ring is formed by the primary amine, that is, the nitrogen atom of the pyrrole ring is coming from the amine in compound in product number 6, and in product number 7 if you see, the pyrrole ring nitrogen is not coming from the primary amine, rather it has to come from the cyanide. Okay, so this reaction must be involving such a mechanism which is going to give us the possibility of getting both these products, in which the pyrrole ring nitrogen is not coming from one particular molecule. So let us look at the mechanism of the reaction, how it is going to be followed. Okay, so in the reaction, both zinc and gold catalyst combination is used, and zinc metal is good at activating nitrogen atoms. Okay, as you can see, the mechanism starts with the activation of the cyanide substituent with the help of the zinc metal. So the cyanide is activated by zinc metal in +2 oxidation state, and then the amine, the primary amine which is aided in the reaction, is going to attack at the carbon atom of the cyanide. Okay, and this is going to result in the formation of this imine. Okay, you have to simply show the electron pushing in this way towards the nitrogen atom, and then this negative charge which is going to be generated is going to take up a proton, and this amine is going to lose a proton to give you this imine formation. So an imine intermediate of this type, which is again containing the terminal alkyne fragment. Now this terminal alkyne is going to be activated by gold catalyst. So if we show the electron pushing, this alkyne is now going to be activated by the gold catalyst, and now you have two possibility of the cyclization, because you have this amine fragment as well as this imine fragment present in the molecule. So you have two different possibilities of getting intramolecular cyclization. Okay, so you just have to simply cyclize the carbocation, cyclize by attacking the carbocation using either amine or imine, and this is how you are going to get two different carbocations 2 and 3. See, if Suppose this imine is attacking at this carbon to give you 5-membered ring. In that case, you are going to get the product number 3. Okay, just look at this part where the imine is joined to the alkyne. And you have another possibility of cyclization, which is this amine. Okay, R2NH is present. So what if R2NH is attacking your alkyne? In that case, you can see that this R2N fragment is joined at the alkyne. So this is how these two intermediate carbocations you are going to generate. Then after this, you simply have to aromatize these two intermediates to get the desired pyrrole products 6 and 7, which are the products given in the reaction. Okay, I hope this mechanism is clear to you. Okay, so a very similar reaction this time. In this case, just if you look at the compound number 24, in the previous question we had the amine written as R2NH2, okay? And in this case, you just have a substituent which is this 4-methoxyphenyl, okay? So the same mechanism is going to be followed, and if you look at the mechanism, this is how the cyanide nitrogen atom will be first activated by the zinc metal, which is in +2 oxidation state, and then it is going to be attacked by the amine, okay, 4-methoxyaniline. And then the gold catalyst is going to activate our alkyne here, and we have the two possibilities of alkyne attack, which is one by imine and the other by amine. Okay, and thus we will get these two different substituted pyrroles product. Let us move to the next question now. Again, if you see, we are starting with an acyclic molecule where protected amine is present, and here you see that 4 or 5 is given. This is nothing but a gold catalyst. Okay, 4 and 5 is just gold catalyst in presence of silver tetrafluoroborate additive, and again we are going to get two different products. Okay, so if you look at the difference of the products, the stereochemistry is one thing, and the major thing which is the difference between these two products is the position of the double bond. Okay, in compound number 2, if you see, the double bond is terminal, but in compound number 3, the double bond has isomerized and it is present as an internal double bond. So the difference between the formation of the product comes from the solvent used in the reaction. Okay, if you use DCM solvent, like here in this case, if you use DCM solvent, then we are going to get the product 2 selectively, and if we are using an alcohol as a solvent in the reaction, we are going to get the product 3. Okay, so let us look at the mechanism how the different product formation is happening. So let us look at the mechanism step by step. So let us start with pathway 1, which is going to give us the product number 2. Okay, so we have this gold catalyst present in the system, which is in +1 oxidation state. Okay, so when we add the protected amine to the reaction medium, we will get the activation of this diene with gold. Okay, in this way. So you see here the cyclization can take place either at this carbon or at this carbon. Okay, so you have a possibility of getting either a 5-membered ring or a 6-membered ring. Okay, but if you notice the stability of 5-membered versus 6-membered cycle, always remember that 5-membered ring cycles are formed preferably. Okay, so in this case also the 5-membered ring will form preferably by the attack of the amine to the gold activated diene. Okay, and you get this intermediate. Now this intermediate upon workup is going to give you the product number 2. And in the product number 2, you have to notice that the alkene which is terminal in the substrate is not going to get isomerized. Okay, so this terminal alkene product you are going to get from pathway 1. Now let us see what happens when we are using alcohol as solvent in the reaction. So in that case, pathway 2 will be followed. Okay, and at first the gold catalyst is going to activate our alcohol which is present in the reaction medium. Now this alcohol is going to form a gold complex of this type due to the activation, and this is now going to react with the amine present in the system. So since the whole gold catalyst is consumed in the activation of the alcohol, the intramolecular cyclization of the diene is going to take place in this way, and we are going to get an isomerization. Okay, because see here, if we look at this substrate present here, initially it is like this. Okay, and H, Pg, and the diene will lie in this way. Okay, so the amine now is going to attack in this carbon, and the ring, the electron pairs will move to the terminal carbon on the side, and you are going to get this particular intermediate product. Okay, so this is now going to simply get deprotonated to give you this product number 3 after workup. Okay, so this is how you get two different mechanism pathways depending on the solvent that we are going to use in the reaction. If we are using aprotic solvent, in that case pathway 1 will be followed and terminal alkene will stay starting from diene. Okay, but if we are going to use protic solvent, in that case pathway 2 will be followed and we are going to get an internal alkene starting from diene. Move to the next question. Now we are going to look at the gold catalyzed activation of allene. Okay, so this is the given allene in presence of this aryl amine, let's say aniline, in presence of gold bromide 10 mole percent catalyst, and the reaction is carried out in THF solvent. Okay, and you can see that this allene is getting attacked by the aromatic amine on this carbon. Okay, and we are going to get this internal alkene. So let us see how gold is activating the allene molecule. Okay, so we are going to start the mechanism from here. Okay, at first the aromatic amine which is present is going to react with our gold catalyst and it will give a salt of this type. Okay, now this salt is going to react with the allene and the gold catalyst is going to activate our allene to give us an intermediate which is labeled as C. Okay, now from C intermediate you can see that the amine which is forming a salt with the gold catalyst will attack at this carbon and the electron pairs will be pushed towards the gold. Okay, and you get an intermediate product of this type which is labeled as D, which can also tautomerize to give you the intermediate E. Okay, so you see that the salt was initially forming a byproduct which is the hydrobromic acid. Now the hydrobromic acid is going to take up a proton from intermediate D or E to give us our desired product, which is the compound number 3, which is containing an internal double bond. Okay, so this is how gold catalyst is going to activate our alene, and it is going to increase the rate of the reaction of attack of amine on alene. I hope this mechanism is clear to you. So again, this is a similar reaction. Again, we have a combination of metal catalyst, which is gold and silver. Okay, and we have this alene here, and again an aromatic amine. So the same kind of mechanism will be followed here. Okay, so I hope you can write this product easily. Okay, but you can simply note down this mechanism. This question must be very easy to you by now. So the mechanism starts from here to give you the intermediate A by the activation of the alene using gold catalyst. Okay, and that is going to give you a positively charged eta 3 gold complex of this type, which is B, and compound B is now going to be attacked by the aromatic amine to give you the internal alkene. Okay, now let us move to this question where the cyclization is happening from the sulfur atom center. Okay, so in this question, what happens? We are using 2 mole percent of gold catalyst in toluene solvent. Okay, so and if you see the product, you will notice that this particular fragment, which is attached to the sulfur atom, has shifted to the carbon atom of the alkyne. Okay, to this carbon of the alkyne, the alkyl chain which is present on sulfur has shifted. So let us see how this mechanism goes. Okay, see, at first the alkyne which is present in the substrate is going to get activated to give you this intermediate. Okay, and the nucleophilic sulfur atom is now going to give you 5 endo tick. Okay, you will see 5 endo decyclization by the sulfur atom, and after the attack we are going to get this cation, which is compound number 10. Now at this position, what will happen? This double bond is going to attack at this carbon, and your sulfur atom will be neutralized. Okay, so we get compound the intermediate product 11 because of the alkyl shift. And now the compound number 11 will undergo aromatization, and you can show the aromatization like this, that this proton will be eliminated and your gold catalyst will go away. Sorry, this bond you can show in this way, that your gold catalyst is going to leave and we get the aromatized product where this alkyl chain has shifted. Okay, so this is how we are going to get the product. Moving to the next question, which is now very easy for you. Net result, if you see, is nothing but the hydroarylation by this phenyl ring to this alkene, which is going to be catalyzed by gold catalyst and silver catalyst present. Okay, so let us see how it is happening. So this is the proposed mechanism. Okay, so let us start it from here. You add gold catalyst to our substrate and we get the activation of the double bond by gold catalyst to get the intermediate C. Now the carbocation intermediate C is going to be attacked by the aryl ring by hydroarylation mechanism. Okay, and we get the intermediate product E. Now E is going to undergo aromatization after losing a proton. Okay, and this is how after the workup we are going to get the product 9, which is our desired product. Okay, so this is the proposed mechanism for this reaction, which is involving hydroarylation. Moving to the next question. So here you see that two different cyclizations are happening as a net result. Okay, because from the substituted indole we are first going to cyclize this alkyne and then we are going to cyclize this alkyne. Okay, and at the end we are going to form a 6-membered ring versus an 8-member heterocyclic ring. Okay, and this reaction is going to be catalyzed by our gold catalyst given. Okay, so let us see how the mechanism is going to happen. So this is the proposed mechanism. Okay, let us go into the mechanism step by step. So at first, when we are going to add our Lewis acid, which is containing gold catalyst, is going to activate our this alkyne. Okay, and the indole ring is going to attack at this alkyne. Okay, and because of this attack we are going to get a 6-member ring. Okay, so basically compound number 6 we are going to get at first, and compound number C is going to undergo deprotonation to give us the aromatization, which is giving us 4 fused cycles now. Okay, now we have the second fragment of alkyne, which is this one. Now this is going to be activated by our gold catalyst. Okay, and now the indole fragment is again going to undergo hydroarylation to give us a 8 endo decyclization, and we are going to get cyclization to get this 8 membered ring. Okay, this 8 membered heterocyclic ring is going to form, and in the workup we are going to get this highly conjugated 5 membered 5 ring containing molecule. Okay, so this is the final product that we are going to get. So this is how both the alkyne fragments present in the substrate is going to react to give us this final product. I hope this mechanism is clear. It is easy. You just have to look at the product in the reaction to see how the hydroarylations are going to happen. Next, another example of hydroarylation, which is catalyzed by gold and silver. Let us see how it is happening. Okay, so the mechanism will start from here. Okay, we are going to add the Lewis acid which is present in the reaction to the alkyne, okay, which is containing a pyrrole substituent in the side chain. So the alkyne is going to get activated by the Lewis acid to give us this intermediate B. And this intermediate B is going to undergo hydroarylation from this pyrrole ring to form this 6-membered ring to give us the intermediate product C. Okay, and in the workup stage, this product is now going to undergo aromatization and dehydration at this position to give us our desired product, compound 67. So this is how we are going to get the cyclized product starting from this propergillic alcohol. Now let us move to a different kind of reaction, which is the epoxidation of tetrasubstituted alkene using iron catalyst. Okay, so 0.1 mole percent of catalyst is enough for this epoxidation reaction, and The reaction is also using hydrogen peroxide as a reagent. Okay, so let us see how this mechanism is taking place. So at first, A is nothing but the catalyst, iron catalyst, which is given in the reaction. Okay, this catalyst is going to be denoted as A. So at first, A catalyst will undergo heterolysis and it is going to produce this intermediate catalyst B, in which the oxidation state of iron catalyst is increased by +2. Okay, initially the iron is present in the catalyst as +2 +3 oxidation state, and at the end of the heterolysis the iron is going to be oxidized to +5 oxidation state. Now this iron catalyst in situ generated is going to react with our alkene. Okay, and if you want to visualize the mechanism, you can visualize it in this way. Okay, so here the oxidation state of iron is in +5 oxidation state, and you can imagine that the oxygen is attacking the alkene, and you can get the intermediate C in the reaction. Okay, now this bond will cleave to give you the catalyst back, in which the iron is in +3 oxidation state, and this epoxide product we are going to get. Okay, so this is how the epoxidation of the tetra substituted double bond is going to take place. So this is another question which is again involving the iron catalyzed epoxidation reaction. Okay, and the reaction mechanism is going to be similar to what we have already studied. Okay, here also we have hydrogen peroxide in the reaction, and 5 more % of iron catalyst is used. So these are the different types of iron catalyst you can see, and in the course of the reaction we are going to get the epoxidation of the double bond. Okay, so moving to the next question. Okay, so this is a very interesting question, which is a multi-component reaction that is giving us a pyrrole ring. Okay, which is completely substituted. Okay, it is in general very difficult to get fully substituted pyrroles or furans, but this particular reaction is giving us this desired product with 38 to 85% yield depending on the substituents, and the reaction is catalyzed by ferric chloride, which is present in only 10 more % amount. Okay, So let us look at the reaction mechanism, which is going to be very, very interesting for this reaction. Okay. So what happens? The reaction starts from here. Okay. At first, this amine and this diketone is going to react to give us this enamine. Okay. As you know, from amine and ketone we can get enamine. So that is the reaction that you will see between this amine and this diketone. Okay. Whereas the two more fragments which are present in the reaction, one of which is aldehyde and the other is nitroalkane. Okay. And aldehyde and nitroalkane can give you a name reaction which is known as Neff reaction. Okay. If you want to revise what is Neff reaction, this is the mechanism which a Neff reaction follows. Okay. So the reaction starts from nitroalkane, which undergoes deprotonation to give this anion. Okay. And this carbon ion attacks the aldehyde to give us this oxyanion. Okay. And this oxyanion reacts with okay. So this oxyanion takes up a proton from the nitroalkane which is present in the reaction, and it gives us this alcohol as the product. Okay. And the reaction is carried out in reflux condition. This can undergo dehydration, which will need a proton to be present at this carbon, and we get an olefin of this type. Okay. R or R dash must be a hydrogen atom to give this dehydrated product. Okay. So this reaction is known as Neff reaction. So if we go back to the reaction, Neff reaction will give you the fragment B by the reaction of aldehyde and nitroalkane, and the amine and diketone is going to give you the enamine intermediate A. And now the nitroalkene and the enamine will undergo reaction to give us this amine intermediate, which is shown here. Okay, the attack is going to happen from this double bond to the double bond of nitroalkene, and we are going to get this amine. Now this 5-membered ring will form because of the attack of this amine at the nitro group, and at the end we are going to get the aromatized product, which is this pyrrole molecule. Okay, so this is how we are going to get this pyrrole, which is highly substituted, and the reaction involved is this multi-component reaction, which is silver catalyzed. Okay, so moving to the next topic, which is cobalt based organometallic reagents, and this reaction is nothing but the well known Poisson-Khan reaction. Okay, let us look at the mechanism how Poisson-Khan reaction takes place. So this is the mechanism which involves catalytic Poisson-Khan cycloaddition reaction between an alkyne and an alkene. So the reaction starts with the insertion of the alkyne with elimination of two equivalents of carbon monoxide to give us this metalla cycle. Okay, and then alkene gets added to the metalla cycle to give us ligand substitution with the elimination of another molecule of carbon monoxide. And after the alkene insertion, we are going to get an intermediate of this type. Okay. Now, carbon monoxide, which was initially eliminated, is going to get inserted again in the metalla cycle between this carbon atom and the cobalt metal. Okay. So, then this metalla cycle will undergo reductive elimination to give us our desired product, which is this alkenone. Okay, and the catalytic cycle will go on. So this is the mechanism of the very well known Poisson-Khan reaction. Okay, so this is how this reaction is following the mechanism to give us this cyclopentenone, starting from this alkyne and this alkene. Okay, so similar reaction mechanism will be followed for these two reactions, where in the first reaction, if you see, we have an alkyne here and an alkene here, and these two will undergo Poisson-Khan cycloaddition reaction to give us this particular cyclopentenone. Okay, and this Poisson-Khan reaction is widely used in the total synthesis of natural products. For example, if you look at this particular reaction, this is used in the total synthesis of daphnylonine B. Okay, and in case of the total synthesis of xylamine A and B, again Poisson-Khan reaction is used between this alkyne and this alkene to get this cyclopentenone fragment. Okay, so this is how Poisson-Khan reaction takes place. So moving to the last question of the session. So here we have an alkene and we are using this fluorinated reagent NFSI in presence of cobalt catalyst, which is this one. Okay, where this cobalt is attached to silane ligands. Okay, and if we look at the net result of the reaction, we will see that this nitrogen atom is getting added to this alkene at this carbon atom. Okay, we will take a short break of 2 minutes and then we are going to resume the session. Okay. Okay, so thank you so much for waiting. Let us resume. So we have this alkene here and this NFSI reagent present in the system, and the net result is cobalt catalyzed attack of this particular nitrogen atom from the amine at this carbon of the alkene. Okay, so let us see how this reaction mechanism is followed. Okay, so the proposed mechanism starts with the reaction of NFSI and the cobalt catalyst. Okay, so NFSI is going to supply the fluorine atom to the cobalt catalyst, which then undergoes reaction with TMDS, which is nothing but this TMDSO present in the system, which is tetramethyl disiloxane, which is often used as protic solvent. So this tetramethyl disiloxane is going to supply this proton to the fluorinated cobalt catalyst. Now, this newly formed cobalt metal complex is going to react with our alkene to undergo reaction to give us the intermediate A. Okay, where this hydride has been donated to the alkene. Okay, and now this particular carbon will coordinate to the cobalt plus 3 complex. Okay, and this intermediate product B is now going to react with this particular intermediate D, which is in situ generated by the reaction of NFSI and our cobalt catalyst. Okay, so because of the reaction between B and D, we are going to get the intermediate salt, which is labeled as C. Okay, and in the C step, you can see that the metal is now oxidized to +4 oxidation state. Now this +4 oxidation state cobalt complex is going to undergo reductive elimination of our desired product amine to go back to its original +2 oxidation state. Okay, and this is how we are going to get our desired product. Okay, so with this we have arrived at the end of the questions included in today's tutorial session. Okay, let us quickly go back and go through all the questions, all the different types of questions that were included in today's tutorial, which were involving different types of organometallic catalysts. At first, we started the reaction with this gold catalyzed hydroamination reaction, and the mechanism. Okay, I'll just change the slide because I have already written a lot of things. So Okay, so in the mechanism we saw the reaction started with the activation of the terminal alkyne with gold to give us this imine 3 by the reaction between activated alkyne and the aryl amine. Okay, and the second fragment of the alkyne was also activated by gold to give us the hydroamination reaction. Then we moved to another hydroamination reaction, which was gold and zinc catalyzed, and we also saw that two different product formation was possible by the hydroamination starting from two different amine fragments. And we also extended the same reaction with this example where we saw the same reaction mechanism to get two different aromatic products. Then we moved to this reaction where we came across another hydroamination reaction in presence of gold and silver catalyst, and the reaction was found to be solvent dependent. Okay, if the reaction is carried out in aprotic solvent, compound number 2 was the product, and in presence of protic solvent, compound number 3 was the product formed. Then we came across this hydroamination reaction of alene, which is gold catalyzed, where we saw that reaction involved the formation of a salt B, which then underwent hydroamination reaction. A similar mechanism we saw here. Again, gold activated the alene, and then the aromatic amine underwent hydroamination, intermolecular hydroamination reaction to give us the alkene. Then we came across this uncommon reactivity where we saw that this alkyl shift from the sulfur atom took place to give us this desired product 2. Then we came across this hydroarylation reaction, which was gold and silver catalyzed, which started with the gold activation of the alkene followed by hydroarylation and aromatization. Again, we saw this reaction which involved two sets of hydroarylation reaction from the indole fragment to give us first a 6-membered ring and then an 8-membered heterocyclic ring. Then we underwent another reaction of hydroarylation starting from this indole fragment at the gold activated alkyne. Then we came across silver catalyzed epoxidation reaction where we saw that the iron catalyzed. We saw that this iron catalyst underwent heterolysis to give us this new catalyst B where the iron metal is present in +5 oxidation state, and that metal catalyst underwent oxygen insertion to give us the epoxide product, which is the desired product. The similar reaction was also found in presence of various iron source catalysts. Then we came across this this multi-component reaction between an amine, an aldehyde, a diketone, and a nitroalkane. Okay, and we saw that first the diketone and the amine undergoes the enamine formation reaction, and the nitroalkane and aldehyde undergoes NEF reaction, whose mechanism also we discussed. Okay, and the ultimate product we got was highly functionalized, highly substituted pyrrole ring. Then we also discussed the mechanism of Pauson-Khand cycloaddition reaction, and we saw that how Poisson-Khan reaction is used in the total synthesis of various natural products like dephnyloline B and xenylamine A and B. And lastly, we discussed this hydroamination reaction, which is cobalt catalyzed, where we got this amine product 13 starting from this alkene. Okay. So with this, we have arrived at the end of this week 10 tutorial. So in the next session, which is going to be our week 11 session, we are going to discuss some more organometallic reagents, which are going to be silver, rhodium, nickel, platinum and iridium based. Okay. So thank you so much for joining for this week 10 tutorial.